Yeah. Sorry for the trouble. I don't know what happened all of a sudden. It went up. I did nothing. Uh-huh. Okay. Okay. So. Okay.
That should be okay now. Sorry about
So
that.
it's to podcast this one.
Because I put it on the right hand one. This one's the podcasting.
Okay. So will this not happen again during the lecture?
We'll try and sort it out.
Hopefully. Yeah. Okay. Okay. All right. Thank you, sir. Thank you. Have a good day. Hello, guys. Can you hear me? I'm sorry. There's a technical problem today. Sorry about the technical problem. Now, once again, I'm really disappointed with the number of people coming to the lab sessions. So please could you come to, there are 2 lab sessions today, and there's 1 lab session tomorrow, right? So please could you come to this, please? Right, and you will get one of these if you come. Yeah? All right. Okay, guys. All right, so I'm really disappointed with the number of people who came yesterday. Shh. So please come to one of the sessions today, Thursday, 12 to 1 to, or Friday, 11 to 12, tomorrow. Okay? All right, on Tuesday, on Tuesday I did 2 examples on bias and MSc. This is, I would just go through, did you follow the second example I did, guys, or no? Let me go through this quickly, if you don't mind. This is the second example I did on Tuesday this week. So here, we were asked to find the bias and the MSc of theta hat, which is the minimum. So I call this to be Z or Z. So the first thing to do for questions like this is to first find the distribution of Z. So first, you start out by finding the CDF of Z, which is this. Okay. And once you find the CDF of Z, then you find the PDF of Z. And for that, you need to differentiate the CDF. So if you differentiate this, you will get this as the PDF, right, of Z. And then you can find the bias. You can find the bias from the PDF, and it turns out the bias, which is defined to be this, is equal to, you get into some integration which uses parts, integration by parts, and if you do that, you will get something, you will get the bias to be equal to 1 over n after some calculations, standard calculations, right? So it follows that the estimator is biased, because remember, a biased estimator is one where the bias is not equal to 0. If the bias is equal to 0, then it's an unbiased estimator. So in this case, because the bias is not equal to 0, it's a biased estimator. However, since the limit is equal to 0, it is asymptotically unbiased. All right? That's the first part I did on Tuesday. The second part of example 2 was to find the MSC. Which, using one of the properties I proved on, last week, you can write the MSC as this plus this, right? And this we already know, which is 1 over n. And the variance you can write like this. You know this from probability 1, okay? And each of these involves integration by parts, and you have to do all the complicated stuff, right? After doing all the complicated stuff, you will get to this. You will get to this, guys, and the MSC turns out to be 2 divided by n squared. Okay? So the limit of the MSC is clearly 0, and hence theta hat is a consistent estimator. So remember, consistent estimator is one where the limit of the MSC as n approaches infinity is 0. So both consistency and unbiasedness are good properties of an estimator. All right, guys. Now what I'm going to do today is I'm going to do more examples. I'll try to do at least as many as possible. So starting with the following. Shh, can you listen, please? Example 3. All right, so here we have a random sample from a Poisson distribution with parameter A, and the estimator for A is the sample mean x bar, and we want to find the bias and the MSC of x bar. Right, I mean of A hat rather, which is equal to x bar. Right. All right, so the first thing is to find the bias of x bar, which is the expectation of x bar. Remember, the definition of bias is the expectation of the estimator minus the parameter that you're trying to estimate. So in this case, the expectation of x bar minus the parameter you're trying to estimate, which is A, right? So this will be the expectation of this, right? Now take the expectation inside, you get this. Now you should know from probability 1 what's the expectation of a Poisson variable. Come on, guys, talk to me. The expectation of a Poisson is A, right? Because this, you know that, right? Oh no, yeah. So this is clearly 0. So what you have is that x bar is an So since the bias is equal to 0, the x bar is an unbiased estimator of A, right? You follow what I've done, guys? Now the second part is to find the MSC of x bar, right? To find the MSC, I will use the formula that I proved last week, which is this. Now we know that the bias is 0. We just proved that the bias is 0. So this guy here is equal to 0. So this becomes the variance of x bar, which is this. Now taking the variance inside, remember 1 over n is a constant. So when you pull a constant outside the variance, what do you need to do? You need to square it, all right? So this becomes 1 over n squared times the sum of the variance of xi. I'm sure you know that the variance of a Poisson variable is A, okay? So this is 1 over n squared times NA. So this is A divided by n, which approaches 0 as n approaches infinity. So hence, x bar is A. Right? So this example is really easy. Are you okay with this, guys? Okay. Now, before I go to example 4, I just forgot about, you guys, did you receive your quiz 4 back? I sent it on Tuesday, but some of the emails did not go through, so I sent it again yesterday. So you must have got your quiz 4 back, right? Did you all get it or no? Yes. Anyway, I just want to give some feedback on quiz 4. I think most of you did well, but some had problems with, simple things, which I talked about at the beginning of this course. Like, if you have a sum, of a constant, right, which does not depend on I, I mentioned this in the class, guys. Don't tell me I didn't mention. What is this equal to? This is n times the constant, right? And also, if you have a sum like this, yeah, constant times xi, then you can take the constant outside of the sum, right? So this would become, so anyway, some of you made mistakes. So I'm reminding you of I mentioned this before in the handwritten note, so just look back. But if you've forgotten, just try to remember this, okay? It's really important. When you come to simplifying sums or products, these kind of inequalities are important, okay? So that's the only feedback. That's the only feedback on quiz 4 I have. And quiz 5 is due next Tuesday, and there was a typo on quiz 5 and 6 which I corrected. So just check my emails, guys. Okay. Okay. Next one. This is example 4. All right. This is similar to example 2, except that here we have a maximum, not a minimum. So you have a random sample from a uniform 0 theta distribution, and we have the maximum of the data as an estimator of theta, right? Okay, so to questions like this, the first thing you must do is try to find the distribution of this, because this is a non-trivial function of data. So you need to start by finding the distribution. When I say distribution, I mean the CDF and the PDF of this, right? Okay, so that's what I will do again. So okay. The CDF of Z is as follows. Right, which is the probability that the max okay, and at this point, okay, if the maximum is less than or equal to little z, then what can you say about each element? Yeah, if the max is less, then each element has to be less, right? Do you find this boring or what? Do you follow me? If you have a sequence of numbers and the largest number is, say, less than 10, then every number in that sequence must be less than 10. Yeah? That's the argument, okay? Now, because we are assuming that x1 to xn are independent, yeah, you can write like this using independence, right? And because we are also assuming that x1 to xn are identically distributed, so using the fact that x1 to xn are identically distributed, you can write this it like this, okay? Now what you have here is the CDF of a uniform. Remember, we are assuming that x1 to xn are uniform 0 theta. Now you should know from probability 1, what's the CDF of a uniform 0 theta? Don't you remember? It's in the formula sheet I gave you on the first day. Is z divided by, you should don't remember, is this is the CDF of a uniform variable from 0 to theta. You remember or no? Okay. Okay, guys, you will think so far? All right. So that's the first step. The second step is to. So that's the CDF of Z. The second step is to find the PDF. So this is just the derivative. It's just the derivative of the CDF. So you should differentiate. You should differentiate that guy here. You get n right. So this is the PDF for Z between 0 and theta. Okay, now the next step is to find the bias. Remember, bias of theta hat, which is the bias of Z, right? Which is the expectation of z minus theta. Now to find the expectation of z, you just need to integrate this guy here, right? So you integrate from 0 to theta of z times okay. I'm sure you've done one semester of calculus, so you should know how to do the integration, unlike me. So if you do the integration, guys, you get theta n plus 1 divided by n plus 1, limits 0 to theta. Correct me if I'm wrong, quite possible. Now the limit at theta is theta n plus 1 divided by n plus 1, and the limit at 0 is 0. Okay, you with me, guys? Okay, now if you simplify this, you get n theta divided by n plus 1 minus theta. And you can simplify this further as minus theta divided by n plus 1. Okay? Are you okay, guys? Yeah? Now this is clearly not equal to 0, so the estimator is biased. However, this, as n approaches infinity, this goes to 0. So theta hat is all right. Theta hat is an asymptotically unbiased, asymptotically unbiased estimator of theta. That's because the bias is not equal to 0, but it does approach to 0 as n approaches infinity. Okay, guys? Are you with me? So that's the first part. The second part is to find the MSC. Okay, to find the MSC, we need to use the property that I proved, which is property number 1. That is okay, guys. So this is going to be the variance of z plus this is the bias we got from over there. Okay, the variance of z, you can write it as like this. The expectation of z, we know what it is, because if you look at the calculations I did here, the expectation of z is this guy here, right? Okay, so this is basically density of right, this is the first term minus the second term is n theta divided by n plus 1 squared, right? Then plus theta squared divided by n plus 1 squared. You see how I got this term here? This from over there. right? So all we need to do is just find this integral here, which is not difficult. So it's going to be n divided by theta n. So this is going to be z n plus 2 . Okay. Now, if you do the calculus here, if you take the limits, you will get. I'm going to do it quickly, so I'm sure all of you know better than me how to do the integration. So I don't need to tell you. So, okay. So this is what you get here, minus. All right, now you need to simplify this. So now you need to simplify this guy here. So I'm gonna pull out n theta squared. So in brackets you have okay, guys. Now this minus this is what? If you do the algebra, once again, you know better than me that this minus this is 1 divided by n plus 2 times n plus 1 squared. Right, so this is plus. All right, now the reason I've done the simplification is because I want to argue what happens to this expression as n approaches infinity. Now, okay, let me ask you, where does this go as n approaches infinity? It goes to 0, right? And this one? As n approaches infinity, this will go to 0, too. Yeah? So the limit of the MSE is 0. So hence, theta hat is a consistent estimator of theta. All right, guys? You have any questions so far, guys? Or are you bored with this? So this is example 4. Example 4. I mean, in the exam, you will get a question on bias and MSC. So you will get at least one question, one full question on bias and MSC. Okay. So that's the reason I'm doing so many examples. Okay, example 5. Come on, guys. this is a slightly different kind of question. So you have a random sample from an exponential distribution, and we have two possible estimators for A, this one and this one. And the question is, which one is the better estimator? Remember what I said to you this week or last week, I can't remember, but if you have two estimators, how do you decide which one is better? The one that is better is the one that has smaller MSC, smaller bias in absolute value, and also smaller MSC, right? So to answer this question, we need to find the bias and MSC of both estimators. Okay? You follow me? Yeah. Okay. So let me put this over here. So I'm gonna find first the bias of A1 hat, which is the expectation of A1 hat minus A. Yeah, this is the definition, right? So this is the expectation of 1 over n minus A. So if you take the expectation inside, you get this. All right, now let me check your memory from probability 1. What's the expected value of exponential variable with parameter 1 over A? Huh? No. Any other answer? No. Come on, guys. Why you forget all this? It should be 1 divided by 1 divided by A minus A. You know, I gave you this formula sheet. Don't you have the formula sheet with you? This one. I gave this to you a long time ago on the first day of classes. Don't you have this with you or what? Don't you have a copy of this? Yeah, just check. So this is 0. So this implies that A1 hat is an unbiased estimator. Of A. All right, are you with me or not? Okay. So that's hopefully here. The next thing we need to do is find the bias of A2 hat, which is the expectation of yeah, you should this is the expectation of xi minus A. So this is 1 over n plus 1 times the sum of A minus A. So this is NA divided by n plus 1 minus A, which is minus A divided by n plus 1. All right, which is not equal to 0. So in terms of bias, so the answer is the following. So in terms of in terms of bias, A1 hat is is the better estimator. Okay. Right, so that's the conclusion in terms of bias, right? Now let's see what happens. Let's see what happens for the MSc. I mean, the conclusion for MSc may be different, but we'll see what happens, all right? So the MSc for A1 hat is the variance of A1 hat plus the bias and we know that this K is 0. Okay. So this is variance of 1 over n okay. Now take the variance inside, guys. You get 1 over n squared times the sum of the variance of xi. Now let me ask you, what's the variance of an exponential? You can check this on this. A squared, yeah. So this would be 1 over n squared plus sum of a squared. So this would be 1 over n squared times na squared, which is a squared divided by n. All right, so let's leave it like this. So this is the MSc for A1 hat. Now let's see what happens for the MSc for A2 hat, guys. Okay, so it's gonna be the variance of A2 hat plus the bias, the square of the bias. Okay, so this is the variance now the bias, we already worked out, we know the bias of A2 hat. If you look over here, this is the bias of A2 hat. Okay, so this is gonna be minus A divided by n plus 1 squared. Take the variance inside, so this is okay, you with me? Now the variance of xi is a squared, so it's going to be n a squared divided by n plus 1 squared plus a squared divided by n plus 1 squared. You with me? Right, now if you simplify this, you get a squared divided by n plus 1. So in summary, the MSc for and the MSc for right. Okay, so which one is smaller? Remember, you prefer the estimator that has the smaller MSc, which is the second. Right, so the the answer you will give is in terms of MSC. Right, in terms of MSC, A2 hat is the better estimator, right? Is that clear, guys? So, as I said, the conclusions can be different. I mean, in terms of bias, A1 hat was the better estimator, but in terms of MSC, that conclusion is not true. A2 hat is the better estimator, so it doesn't need to be the same, right? It can be different with respect to the two criteria, right? So, any questions on this, guys? All right. Don't be in a hurry, guys. I have plenty of chocolates for you later, so you don't need to go for lunch. Huh? No. All right. This is probably the last example 6. Shh. Right, so in this is slightly different because in this example, can you listen please? In this example, you only have one data point, which is x. Instead of a sample of n data points, you have just a single data from a binomial distribution. Oh man, I think I'm sleeping today. It's not x. It shouldn't be x, guys. It should be is n, okay, not x. N comma p, right? N comma p, and let p hat be an estimator of p, right? So we want to find the bias and the MSC. So the bias of p hat is the expectation of this is 1 over n times the expectation of x minus p. Now, the expectation of a binomial is, come on guys, talk to me, n times p minus p, right? So this is p minus p, which is 0. So p hat is an unbiased okay. So that's the first part. The second part is to find the MSC. MSC of p hat is by property 1. We can write this as the variance of p hat plus the square of the bias. And this guy is 0, so this is the variance of x by n, okay, which is 1 over n squared times the variance of x, and which is 1 over n squared times n p 1 minus p, which is p. All right, guys. Okay, so that's example 6. So you should be able to do quiz 5, right, and hand it to me possibly on Monday. Next week we will start doing maximum likelihood. Maximum likelihood is a method for constructing estimators, right? We will start talking about that next week, guys. But please do come to the lab sessions today or tomorrow, all right? R is very, very, very important, guys. It will get you jobs. Sorry, ma'am.
No,
sorry
you're all right.
to take.
It's only.
The computers are playing.
Do you have any students with queries before an assignment? My
All the-
office
all the-
hours are
all-
very, very busy at the moment.
All the time, yeah. I am teaching like a 400 students class. How many students are in yours?
300.
See you later.
See you later. See you next week.